Welcome back to the second part of this lesson on proofs by induction. Here we go. I've already gotten the board ready with the induction proof template, which we had covered at the end of the last lesson. Here it is in slightly abbreviated form. Remember, what we're trying to do is we're trying to prove a universal statement about all positive integers, p of n, say, using this induction axiom, which created this template. And recall, we've got these two steps. We've got the base case, where we have to prove p of 1, whatever statement that is. And in the induction step, we have to fix an arbitrary n. I called it n naught before. That gets too cluttered after a while. You're certainly allowed to refer to it as just n, realizing it's a constant from this point forward, generic constant. You assume one particular statement, p of n, corresponding to that constant value of n, and then you prove the next instance of the statement, p of n plus 1. And that's the end of that template. Just below, for reference, I've also recorded the recursive definition of sums, because our first few proofs will be using that. And I want to jump right into an example here of a proof by induction. So an induction is very useful for establishing, among many other things, summation formulas that you might need for analysis of algorithms, or in all sorts of places these things come up. In the book, I do, as an example, the sum of the first n odd integers. Here I'll look at the even integers. So the formula is sum k equals 1 to n 2k, and the claim is that that's going to be equal to n times n plus 1. And I forgot the quantifier. This is supposed to be true for every positive integer n. Sneak that in right there. And so this entire formula, this sum, and the left side is equal to the right side, that's a statement that involves n. An open sentence, if you like. So this thing in the box is p of n, the whole formula. And before the proof, if you just want a little example, so over here, if n is 4, say, and we expand out the definition, I have a 2k, so I'm going to start with 2, and then I get 4, 6, 8 on the left side. 2 plus 4 plus 6 plus 8. And if you just calculate that, you get 20, which is, in fact, 4 times 5. Just as a little example of what the formula is telling you. It's adding up even integers, positive even integers. But this is going to work, so we just, I guess, proved it for 4, but that doesn't work with how you're going to prove infinitely many instances of this formula. You've got to do induction. All right, so let's start with the proof now. Proof. And because the clue of it, when you use induction, if you have a recursively defined concept with a base case and a recursive case in the definition, this is the definition right here, well then you're probably going to need induction as to prove anything about it. So let's try it. So say we use induction on n. We're just going to slavishly copy the proof template. Induction on n, and let's do the base case. It's good to label things. We called it part 1 or part 2, but in induction proofs it's just usually called the base case. So prove p of 1. So again, we've got this formula here, but we have to make a substitution. Everywhere I see an n, I'm going to have to put a 1 to find out what the formula says in that case. It's saying the sum k goes from 1 to 1 of 2k is equal to 1 times 1 plus 1. Okay. And this is going to be easy as long as we realize that we can't use this equation in the proof. This is the goal. We don't know it just yet. And so what we have to do instead is go back over here. By the way, what is AK in this situation? AK is 2k, 2 times k. All right. So now, and we're going to do this little thing where we look at the left side and just calculate it. Compute sum k equals 1 to 1 of 2k. Well, that's just going to be a sub 1. All right, so I put a 1 in for k, and I get 2 times 1. And, okay, so that's by definition of sums. That's just by the base case of the definition. And 2 times 1 is 2 by arithmetic. And then, of course, this is also equal to 2. But I'm going to actually write it out in the form of what we call the chain proof, where I've started at the left side of the goal, did a bunch of stuff, arithmetic, definition, sums, and I got to the right side of the goal. I have therefore proved the goal by the chaining together all of the known equalities, right? So there's the base case. And usually the base case isn't a big deal, and then except for these little logical nuances. It's the induction step you have to worry about a little more. Let's take a look at that. All right, and we're going to follow the outline. Now we have to fix an arbitrary n, positive integer n. You can call it n naught, but you'll see there's all sorts of subscripts that get in the way, so just call it n. And now we actually get to assume the very thing we thought we were proving. Again, that's not circular because we're only assuming one instance of it for this one constant value of n out of the infinitely many summation formulas that this contains. We only assume one of them, a generic one, admittedly. All right, so it's this very thing for the particular value of n that we just fixed. We're allowed to assume it works. Okay. But then we have to do something. We have to prove the next one. The next instance, where we go up to n plus 1, all right, you have to be careful. So everywhere I see an n, to get p of n plus 1, like this and these n's also have to get substituted and replaced by n plus 1, which on the right side produces n plus 1 times n plus 1 plus 1. Which is n plus 2, but to show you the substitution, I'm leaving it in that form. All right, so there's the goal. Not the same equation as this one, because it's a different value of n. And so we have to do it. I mean, we didn't assume this. Okay, how are we going to do it? Well, we're proving an equality of two numbers. Let's try a chain proof there as well. I guess I'll get rid of this. Again, this use of board is a little awkward, so I want to keep this stuff around for a little while. So I'll do it over here. So say use a chain proof, a chain of equalities. And we can say something like, we know, and what we're going to do, we're going to start with the left side of the goal, and not say this, which isn't known yet. We're going to start with the left, do stuff we do know, until we hopefully reach this. And every step should have some kind of a reason. So k equals 1 to n plus 1 of 2k. What do I know about that? Basically nothing, except this. This is the definition of sums at the beginning. That's really all I know. So let's do it. Let's use that. So by definition, the sum up to n plus 1 of whatever term is the sum up to n of that same term, 2k. But then we have to add in a sub n plus 1. Okay, and I guess I just erased it. So ak was 2k in this situation for any choice of k. This is for all k. So replacing the n plus 1, k is n plus 1. So I have to add, the thing that gets added in is 2 times n plus 1. It seems like I'm belaboring that a little bit. That often causes confusion. People aren't sure what I'm supposed to add in there. You have to know what a k is. Okay. So this is by definition of sums, the recursive part of the definition. That's the reason this is known. Okay. And so we have this. Now, what do we do with this? Well, we actually have an assumption. This is why the induction is so neat. this thing that's shown up here is the very sum that I assumed to be equal to this. Okay, so I can use that right there without worrying and replace that part by that, and I still have this extra part. And so this step is true. Remember, we call the assumption was called the induction hypothesis. You always want to flag inside the proof when you're probably going to use this somewhere. You say, exactly where am I using it? Well, right there to go from here to here. Okay, and then that's part is still the same. And now we're going to say, okay, well, we want to get this. We got that, and we can keep. It doesn't quite match yet, but we can do some algebra now. And we might notice that both pieces have an n+1 that can be factored out, which produces, there's an n here and a 2 there, so n+2. So you can factor, and then, just to make it look exactly like the right side of the goal, we remember that 2 is 1 + 1, and so on. Associativity, whatever. Let's say by algebra. You could be more specific there. And we did it. We got to the right side of the goal, and from the left side, with equalities that are known. So that's the end of that proof. That's the end of the induction step. We've completely done it. How about that? All right, and I guess since there is a little corner of board still left, there's a sort of an interesting picture. Sometimes some of these formulas have pictures that go along with them. We did I think it was the n=4 case. Here's 2 squares. Just to quickly show you this kind of neat picture here. 2 unit squares, and this is supposed to represent essentially 4 more squares that are right next to those. And you can draw some more. There's 6 more guys. And 8. So how many squares? On one hand, there's 2 + 4 + 6 + 8 squares by looking at these like ribbons individually. But on the other hand, I've just made a rectangle of height 4 and width 5. So by doing it that way, 4 times 5, you get 20. And that's also 20. Oh, anyway, in general, you'd have an n and n+1 if you create it like this. So that's supposed to be a visual proof of this identity. Trouble with that is I've really only proved P of 4 right here by this picture. And if you wanted to prove the whole thing for every n, you'd find yourself drawing a similar picture, but at some point you'd have a ... in your picture, and so that isn't really allowed as an official proof valid for every n. You do need this induction technique. All right, but it's still some compelling if you're trying to remember the formula. Sometimes there's a sort of a neat way of seeing it. All right, so that's the first example. Let's see how, okay, good, so that's good. Try to do 3 examples in this particular video. And for the next one, let's do a general property of sums. Rather than having a specific sum with like 2k in there, let's try to prove the following. For all c and ak, say in the reals, and for all positive integers n, here's a neat property of sums. If you take c times the sum, k goes from 1 to n, of ak, you're allowed to move the c inside the sum. Like that. And whether or not it looks like it, this is secretly sort of a generalization of the distributive law. Again, just for a second, let's write a case of this so you can see what it looks like without summation notation. So if we were adding 4 terms together, and multiplying the whole thing by c, then by algebra, you could sort of distribute the c and do it like this. And so that's the n equals 4 instance of this, but we want to prove it for every n. All right, so we can't just sort of write this down without having a dot, dot, dot or something that isn't allowed. All right, so we need induction to officially prove this. Once we prove it, though, we can use this property in later proofs involving sums. So proof. Oh, but before we even get there, we have to deal with all this. So we have to fix the stuff, fix arbitrary c and ak in the reals, these terms, and this number that you're multiplying. I won't fix n, however, not right away, because for that part we're going to use this, and we don't actually do that fixing until we get to the induction step. Why am I doing induction? Because we have this sum, which is a recursively defined concept. So at this point, having gotten through this part, now I'm going to say that we use induction on n. And launch into all the stuff. So base case, and so on. Of course, you're going to have this template completely memorized before you try to make your own induction proofs. Proof P of 1, and what's P of 1, or P of n, first of all? This entire formula involving these constants, there's also this n, which shows up right here. That's the formula. So for the base case, we're going to take that formula, but everywhere I see an n, I'm going to put a 1. Which creates some strange looking things, but that's what it is. And how do we prove that? Well, we're going to use a chain proof. We know, logical status word there. What do we know? So let's think about what we know about the left side. Pretty much nothing other than the definition. Sum k equals 1 of 1 of ak is a1. Multiplied by c. And parentheses there, I mean, it's just because I substituted in right here, right? Don't need those parentheses. But then the key realization is, well, that is also the base case of the definition of this guy, where the c is inside. So in each case, I was using the base case of the definition of sums. There isn't even a sum. It's just replacing the k, the subscript, this summation index, as it's called, by 1. All right, so that's, again, base case isn't usually hard. You just have to make sure you don't get confused by it. But there it is. We finished the base case. Let's do the induction step. All right, so following template, we're doing something for every positive integer n. Let's fix a particular one. Use a slightly different phrase here. All sorts of variations of how you can say this, as long as you say something that means this. Okay, fix a particular positive integer n, which is now constant. Assume p of n, which is here. We just get to copy the statement unchanged. C times sum k equals 1 to n, ak, is sum k equals 1 to n, ck. And we're going to then prove the same thing, but everywhere the n showed up, it's now going to be p of n plus 1. So these upper limits are going to be n plus 1, but everything else is the same in this goal. I hope this is visible. Again, so little board space available to us. so that there's the assumption, there's the goal, two different instances of the general formula, and we can do another chain proof to execute the induction step. Chain of equalities. You're going to see these all over the place in this section. All right, so again, we know, right? Have to know the individual links. We have to start here, not use this, start here, and use stuff we do know, until we get to here. All right, so copy the left side down. And then what do? Well, the only thing I know, really, about the left side is this recursive definition of sums. And there's also this C multiplying the whole thing. All right, don't really need those parentheses, but just for emphasis, I'll put them in. Here we do need them. So now this turns into the sum k equals 1 to n of ak. Put lots of parentheses, plus a sub n plus 1. So that's by recursive definition of sums. That's why that's true. Now, what do I do now? So what is this? Okay, let's stop for a second. What is this? This is a number, C, times the sum of two numbers. This sum in the end is just a number, a real number. So recall, for instance, by the distributive law for the reals, if I just had two numbers, like this, C times S plus T, we had an axiom about the real numbers that said that's C times S plus C times T. And that's exactly, and for every C, for every C, for every S, for every T in the reals, that was true. Okay. Well, that's the situation we're in. Realizing this is a number, it's a real number, S, and here's another one, and we're multiplying by C. So by just the regular distributive axiom that only has two things here, we're allowed to say that this is C times this first number, which happens to be a sum, but oh well, and then plus C times the second number. So this is by the distributive law for two things, two summands. The one I just mentioned right here. Again, that's an axiom. You have to prove that. Okay, and you do have to keep track of where all the parentheses and the C's are, right? So something happened there. Now there's two C's. Okay, and now something else is about to happen. I'll write it first. And ask everyone to think about what just happened and why is that allowed? What just happened is the C has moved inside this sum. It's C times the sum. Here it's the sum of the C times the AKs. Why is that allowed? The answer is we assumed that you could do that for n. I'm doing for n, not for n plus 1 right here. So that is the exact moment in the proof where the induction hypothesis gets used. Okay. And then we're almost there, actually, because now what were we trying to get to? We're trying to get here, this side. And this is also a recursively defined thing. And if you write down the definition of what does this mean, you get the sum from 1 to n of this term plus the last term, where k is replaced by n plus 1, and still having the c in there, which is this. So this, by using that definition sort of backwards, it's an equation, it works both ways, forwards and backwards, so to speak. You can change that back into the defined concept, sum 1 to n plus 1 of c times ak. Now the ak in my definition is now c times ak. All right, so I hope this is all visible. But anyway, so we got from the left side of the goal here, we did known things. We had a reason for everything. This is the reason for that, by the way. And we got to the right side of the goal, so we did it. That's a chain proof of this equation, completing the induction step and completing the proof. All right, great. So we're still good on time. Let's do one more as promised. And now, maybe it's safe to erase this now. You've all memorized it by now. So we did two proofs that had sums, but there's many other kinds of things you can do that have induction in them. It's not always sums. And in this particular third example, wherever it went, here it is, we're going to have a sequence. So here's what this is going to look like. So the sequence will be called A sub n. There's going to be a term A sub n for every positive integer. And A1 is defined to be 3. Just tell you what that one is. But then for the other sequence terms, I'll tell you that A sub n plus 1, the n plus first term, is recursively 2 times the previous term an minus 1 for every positive integer n. Okay, so this is what's called a recursively defined sequence. I'm not adding anything up here, but I just have these terms lying around. And we kind of like to know what this is. So before proving anything, just to get used to, it's a new definition, which is just enforced for this one problem, this sequence I've just defined. But you can execute this recursive definition and figure out, like what's A2, for instance. So A2, if you let n equal 1 in my recursion, is 2 times A1 minus 1. But A1 we already know is 3. So now we know that A2 is 5. And once you know that, well, you can get A3. By the very same recursion, 2 times 5 minus 1 is 9. You can get A4. So 17. And in general, you just take the previous number, double it, subtract 1. So I'll do that just more quickly. So 34 minus 1 is 33. 33 times 2, 66. Minus 1 is 65. Dot, dot, dot. All right. And the hope is, like maybe this is describing the running time of some algorithm as a function of the input size or something. What you'd really like is sort of a non-recursive explicit formula for these numbers that are coming out, starting with 3. So the sequence we've got is 3, 5, 9. So far are these terms. And this is a 1, 2, 3, and so on. So here's n and here's an. And what you want to ask is there some pattern to these values? Okay. And it's like one of these IQ questions, like if you look closely and think about it for enough, you might notice, you may or may not notice, that these are very close to powers of 2. In fact, what seems to be true, based on the data so far, is that A sub n is just 2 to the n plus 1, like this. 1 more than 2 to the n, because 2 to the n would be 2, 4, 8, 16, 32, 64. And so this is true for for all the values I've calculated so far. It seems to be true. And it is true for these, but how do I know it's always true? The thing that's always true by definition is this. And this is the thing that we have noticed, which we could now try to prove. All right? And so this is a very typical way of using induction where you have some pattern that emerges from the first few values of n, and then you want to prove it. So now let's do that. So let's prove that for every positive integer n, that my guess actually is the right thing. That's what I would like to do. And because the sequence came to us as a recursively defined thing, it's natural to try to use induction. All right. So we follow the steps, do the base case. But it's not a sum anymore. All right, but that's okay. So P of n here is this thing. It's the assertion that the nth term really is 2 to the n plus 1. So P of 1 would ask us to prove that A1 is 2 to the 1 plus 1. You should resist the temptation to say, oh, that's 3. We'll do that in a second, but the goal should be kept separate from the proof of the goal. So here I just substituted and did nothing else. Okay. To prove this, we'll do a little calculation, a little chain proof, starting with what we know. And the only thing we know about A1 is the definition. It's defined to be 3 by definition. Base case of the definition. But of course, 3 is 2 plus 1, know that, and then 2 to the 1 is 2, we know that. Say by definition of exponents. I won't list all the reasons here, but we got it. All right, both sides are 3. So the base case is done. Easy, usually, but it has to be done. It's logically required. Wait, that wasn't it. Okay. So on to the induction step. Okay, so we follow the rules. We fix an arbitrary n. Fix a positive integer n. We assume P of n. Noting carefully, this formula is the goal. So we get to assume an instance of it, a fixed particular instance, and then we have to prove the next instance. We have to prove that a n plus 1 is 2 to the n plus 1 plus 1. 1 outside the exponent, by the way. All right, so that's what we have to do. And how do we do it? Well, once again, it's equals, so we're going to do a chain proof. Chain of equalities that leads from the left side of the goal to the right side. All right, with the status word as well. To introduce the chain, you never just write an equation in a proof with no status. Okay, that wouldn't be allowed. All right, so here we go. So we know, we don't know this. This is the goal. What do we know? We know nothing about this, an plus 1, at the moment, except the definition. It's the only thing we know, recursive definition. So that's basically the only thing we could say to get the chain going. And this definition is just from this one problem, okay, but still a definition. It's used the same way as everything else. Maybe in the next problem will be another definition of another sequence. All right, but this is what it is. All right, and what now? Well, we assumed what an is this. That's the induction hypothesis. So I can just substitute that in. 2 times, and then I put 2 to the n plus 1. And then minus 1. This is equal to that. So that's induction hypothesis used right there. You always want to, again, show where you're using it, how you're using it. And that's great, but okay, we haven't yet reached the right side yet, so now we have to do a little more stuff. Distributive Law of Algebra is still available to us, so I can do that. 2 times this plus 2 times that. Still a -1 on the outside. And then, actually, this is kind of neat because this brings in this recursive definition that we had. If you remember, how do you define x to the n or x to the n plus 1? You see that this is going to turn into a 2 to the n plus 1 by use of that definition. And this is, of course, 2. I'm showing more detail than maybe we really need, but whatever. It's always good to show steps and a little bit of arithmetic here. And a period. And look, we've reached the right side of the goal, starting from the left side and doing known things, each of which had a reason. So we finished the induction step. All right, so that's the end of that example. That's also the end of this video. There'll be another video at some point with even more examples of induction proofs. See you next time.